Welcome. We're going to be talking about recursive algorithms today. So the first part is about the computational model on the recursive thinking. So the way that we think that way in order to solve problems. So in order to do that, let's talk about a game, which is called the Towers of Hanoi. And this is the game. The goal is to move the whole tower. The tower is comprised of several disks, and the goal is to move the whole tower from one peg to another peg. Now, the rules of the game are that we have to move one disk at a time only, and we cannot put a larger disk on top of a smaller one. And so that way we have to go step by step and move the whole tower from one to the other. So let's play and let's see how we can do this. I'm going to put it in here so that you can see it. Okay. So we want to play the Towers of Hanoi. And so the whole idea is to move according to the rules, is to move the tower. So I can move one over here. Then if I want to move this one, I cannot put it here. So I would have to put it there. But then I can't move this one because it would be larger than any of the other ones. So I can move back this one, but I'm back to where I started. So obviously, this is not a straightforward game to play. But hang on. Yeah, right. Meet Nina. She says that she can do it with 4 of them. I've got 5 in here. So I'm thinking, well, if Nina can do 4, then I can ask Nina to move 4 over this peg, and then I will just move the last one, and then I can hire her again. So Nina, can I hire you? And she says, yeah. So can you please move these 4 pegs, these 4 disks, from peg 1 to peg 2. She says, yeah, I can do that. But Nina doesn't really know how to do that. So Jamal. So here comes Jamal. And Jamal says, what? And she says, can you move the 3 pegs on top from this peg to that one peg? Yeah, I can do that. Yeah, I know how to do that. Okay, so do it, please. And then you call me. So Jamal is going to move these 3 pegs that are on top, and he needs to move them from here to the middle one, but he doesn't really know how to do that. So Pedro, come over. Yep. So Pedro says, okay, what do you need? I need you to move the 2 smaller ones from this peg to that peg. And Pedro says, yeah, I know how to do that. So he goes this way, and then that way, and then that way. And I'm done. Oh, thank you very much. No, hang on, but I charge $1 every time I move a disk. Yeah, don't worry about it. Okay, so now Jamal moves this one in here, and he says, now, Pedro, I need to hire you again. So can you please move these 2 from the 3rd peg to the 2nd one again? Yes, again, please. Okay, yeah, no worries. So Pedro goes and does this thing. And so Jamal is done, or so he thinks. And he's, Nina, I've done it. Nina says, okay. So Nina moves this one and says, now, could you please move this tower from peg number 2 to peg number 3? Again? Yes, again. Pedro, hey, I charge $1, but yeah, I know. Don't worry, we will invoice the professor. Okay. So Jamal changes this. Jamal is going to change this from there to there to there. And I'm done. So now Jamal moves this one in here, and he asks Pedro to do it again. So Pedro does that again, and he moves this one over here. And then Jamal says, I'm done. Oh, so he's done. And then Nina comes to me and says, I'm done. So what I'm going to say is, okay, fine. So now I want you to move the tower from peg number 3 to peg number 1. And you can pretty much imagine the rest of it. So this is basically recursive thinking. And in recursive thinking, what we're trying to do is to say, can we simplify the problem to make it a little bit smaller than it looks? And then the idea of having subcontractors will help the moment that we see the recursion trees and the analysis of the algorithms, because we're thinking about stages. So in this case, I just took these 3 things. And so I have one that I call Nina, the other one Jamal, the other one Pedro, and each one of them is going to be in charge of one of the levels of what is going to be the recursion tree when we describe the algorithm in that way. But it helps to think about, contractors and subcontractors, and how many times do you have to ask one or the other person to actually do it. So now we've done the towers of Hanoi, and the basic thinking is the following. The basic thinking in recursion is, if I can move a tower with n-1 disks following the rules, then I can also move a tower with n disks. This type of thinking is what is encompassed in the methodology, in the logical methodology of mathematical induction. It is the most important step when we're using mathematical induction for proving things. Is if I can do something for n-1, then I build it for n. So I prove that I can also do it for n. The proof is here visual. It basically says, first of all, we move the n-1st tower, which would be in the little picture here. That tower we have is this one in the top. So we move this n-1 tower from the red peg to the green peg. Once it's in the green peg, so that's step number 1. Once it is in the green step, I move the bigger disk into the blue peg, and then I have to move again the n-1, the tower with n-1 disks, and I have to move it on top of the one that I just placed. So the assumption is that we do know how to move this n-1 disks. And that's what I exemplified with the idea of the subcontractors. So if someone can do it with n-1 disks, then I know what the solution is. And of course, the whole idea of recursive thinking is that we need to be repeating this until we get to what in mathematical induction we call the base case. And in some of the contexts, we're going to call it the initial conditions, which is, in this case, I exemplified with Pedro that he knows how to move 2 disks. Normally, we go down to 1 disk. That's the trivial or base case. We do know how to do 1 disk. Most people would know how to do 1 disk. So this is at the basis of what is recursive thinking. Okay, the towers of Hanoi were actually invented by a mathematician in order to illustrate the concept of recursion. So he made up this game. Lucas is known for his study of the Fibonacci sequence. The related Lucas sequences and Lucas numbers are named after him. So he was doing a lot of number theory. And he's also famous for being the creator of mathematical puzzles, of which the Tower of Hanoi that I just showed you a while ago is very popular. The recursion is, of course, not exclusive of computer science and mathematics. If you actually go to Google and you Google recursion, the first thing you find is that Google is asking you if you meant recursion. And when you click on that link, it brings you back to the same page. And Donald Knuth, a very famous computer scientist, is known to have said that in order to understand recursion, you must first understand recursion. This is a very nice visual because, of course, in that it was in the Netherlands in the 1940s that they were selling this chocolate. And in the box of chocolate, there's this lady that is bringing on a tray a box of chocolate. But of course, the box in the box also has a box, a lady carrying a box. And the box in the box in the box also has a lady carrying the box, and so on. So it is a very nice visual for recursive thinking. Recursion, recursive thought is not a modern thing. One of the first mathematical thinking, mathematical applications of recursive thinking is what we now know as Euclid's algorithm to find the greatest common divisor between two integers. The way that Euclid was thinking, and we know that because we've seen his writings, the greatest common divisor is, of course, the integer that the greatest integer that divides both of the arguments. So here in the figure, I have depicted a rectangle. And in this rectangle, the very small squares represent 1 unit. So it would be 1 integer. So the length, the vertical length is A, which is an integer A, and that's the size of the vertical side. And the size of the horizontal side is B. Now, in this figure, if we divide A by B, we are going to obtain, this is a square that this whole square is size B by B, and this other square, I'm putting it a little bit smaller so that you can see what I'm annotating. So we can fit the squares B by B twice in A, but there is still a remainder. So we call R the remainder. And this is the way that we denote the notation. We say that the remainder of dividing A by B is equal to R. R is the remainder. And it's very useful in many, in this area to use mathematical results and theorems. The lemma says, if A is bigger than B, then the greatest common divisor between A and B is the same thing as the greatest common divisor between B, which is the smaller dimension, and the remainder of A divided by B, which is R, which I have illustrated here by this arrow, saying in order to solve the original problem, which is the big problem on the left, it's enough to solve the problem with a smaller rectangle, which is the rectangle on the right. And so we proceed by solving smaller problems at each of the steps, very much in the same way that I illustrated the towers of Hanoi. And we can think about doing a recursive programming. I'm showing here the pseudocode. And the way that this recursive thinking goes into code for computing is very, very similar to the box of the chocolate. It defines a function GCD, which in the definition of this function, it calls the function. I'm really sorry. I'm going to have to stop a little bit of an interruption. I'm sorry about that. All right, so who was Euclid? Well, Euclid of Alexandria lived around 300 BC. So as I said, recursive thinking is not modern times. We have recursive thinking already. And in this parchment that has been found, that is alleged to Euclid, you can see how he was making all these calculations with the geometry and number theory. But he basically is the creator of what we now call the Euclid algorithm. And it's interesting to see that applications of this Euclid's algorithm for the greatest common divisor include, among others, the basis of today's cryptography. So we use a lot of the recursive algorithms. In this example too, we are going to show the merge sort algorithm. The goal is to sort an array of integers. Well, it doesn't really have to be integers, but for this lecture, we're going to assume that everything is integers. Now, each time that a card is placed in the array, say that it costs $1. So we would like to do it in a relatively efficient way, well, in the best efficient way possible. So think about recursion. How can we solve the original problem if we have already solved smaller problems? So suppose that we have solved 2 smaller problems with subarrays, and then we need to merge them. So if they are already sorted, we need to figure out, can we do that? And for that, I'm going to show you a YouTube video. I prepared this video some time ago. It's in YouTube, and I'm going to play it now a little bit faster than usual because it's important that we can move along. And I think it was a little bit slow. So this is the video. I'm going to take out my image.
I'm going to illustrate now the merge step on the well-known merge sort algorithm for sorting arrays. This merge part supposes that we have 2 already ordered arrays, and we have to merge them into one ordered final array. So what the algorithm does is that it considers the already ordered arrays as 2 different lists or piles. So these are subarrays, or I call them piles because I see them as tiles. So what the algorithm does is that it starts comparing just the top card of each of them. So the one that is smaller is placed in the first place in the final for the final array. The second one, again, pile number 1 is the one that has the smallest one. So this one places in the second step. Now, as I'm doing this, it's very important that you realize that in the algorithm theory, one of the important things is how much computational time the algorithm is taking. So how many operations am I doing? And so I'm always comparing, and I'm always just picking one card out of each of the piles to place it on the actual final array on the place where it goes. Then I compare these 2. In this case, this one is the one that goes next. And the next one is pile number 1, 6. The next one is pile number 7, the one that has the smallest one. Next one is pile number 1 that has the smaller one, which is 8. And the final one is 9. And so we see at the end, the merged array is already sorted. And this is what we wanted. But also, it should be easier to understand why we say that this step takes linear time. That is, the number of placements that I have to do, the number of comparisons that I have to do is exactly the same as the total number of cards in the 2 piles.
So that's the merge part of the algorithm. And now what we're going to see.
Hello there, everyone, and welcome back to the Closet Historian in my sewing room, where today I'm going to be answering the age-old existential question: why darts? What even is a dart? How do I get them?
I'm sorry. Yeah, I thought I had my other video after that, but sorry about that. It was a different video. So anyways, we know now how to merge 2 arrays that are themselves ordered and how to merge them in a very efficient way. So how do we use this in order to use recursive thinking and solve the original problem? For that, I'm going to show you the next video, which is another one that I also prepared beforehand. And this is the video for how to put together the merge part with the idea of recursion. Again, the idea of subcontracting and so on. So this is the merge sort algorithm.
We have already seen the algorithm merge, which merges 2 lists that are already sorted, and it does this in linear time. So now we're going to illustrate how a recursive programming algorithm works. And this is the merge sort algorithm that I'm going to illustrate. So the lines of code are usually quite simple in recursive programming. They're very short, but the number of evaluations of the basic functions can become quite complicated for analysis. So we call it recursive because it calls itself. The algorithm merge sort has arguments. A is an array, P is the left index of the array, and R is the right index. So for example, here it would be 1, 2, 3, 4, 5, 6, 7, 8. So P would be 1 and R would be 8. Then The algorithm, what it does when we call these type of algorithms divide and conquer algorithms, because they try to do the job in smaller sizes. So what this does is calculate the midpoint. In this case, because they're A, the midpoint would be leaving 4 on one side and 4 on the other. So that's the midpoint of that array. And then it calls the same function. So it is a call to the same function, and that's the recursive part of it. It calls the function for the left array from P to Q, say from 1 to 4, and it calls it for the right array, say from 5 to 8. And then it calls the merging of those two. So if these are sorted, then we have to merge them. So I'm going to illustrate how the algorithm actually looks like, how the compiler would do it in using an analogy. So the analogy that I'm going to use is that I want to solve this problem, but I don't know how to solve it. It's too complicated. So then I have a friend, Sam, and Sam is telling me that she can solve it, but she can solve only smaller ones. So she is going to do half and half. So that's the divide part. So she's going to do 4 on one side, 4 on the other. And then, of course, she's going to be using the merge algorithm to deliver. So she says, yes, I can do it. But she really doesn't know how to do it. She says, if I could just sort these two piles, it would be, then I can do the merge. Merge, I understand. So she says, but how do I do this? So here comes Alex. Alex says, no, I can help you because I can do it in smaller parts. So I'll do it in groups of 2. So Alex has to do 4 times the job. And he says, yes, I can deliver, because then he can do the merging really easy. And then he can deliver. So the promise that he has to Sam is that he will deliver 2 already ordered lists. And then, of course, he can merge them. And then she can give me the final job. And of course, as you probably have already guessed, Alex doesn't know. So another subcontracting. Alex says to Paul, I need to do this. And Paul says, yes, I can do that. So Paul considers each one of the cards, and this is, of course, where the middle point in groups of 2 is just considering groups of 1 at a time. So for groups of 1, they're already sorted. And because they're already sorted, then Paul says, I'm ready to deliver to Alex. I promised Alex that I was going to deliver pairs that are ordered. So now Paul uses the merge algorithm that says you take the top card on each of the piles and you put the smaller one in the left and the other one on the right. And so this is already ordered. So he's already ordering. So this one goes like that. And that one is ordered. So he delivers to Alex what he promised, which was 4 lists, but already ordered numbers. So Alex says, now I know how to do that, because now I only just need to use the algorithm for merging these cards. And the algorithm for merging, which we have discussed already, is in merging these 2, just take the top one and you compare. So you put the smaller one on the left, and then followed by the next one, followed by the next one, and the next one. That's sorted. And for this pile, he again looks at the sorted lists or piles, and so he puts them in order. So this is the first one that comes, then comes that one, comes that one, and then comes that. So Sam is almost done. Sam says, okay, now I can pay Alex and everything's fine, but now I need to deliver the final answer. And the final answer, of course, is to merge these piles. And merging these piles, that is done again, remember, in linear time. So the final answer is just to pick the smaller of the top cards on each of the piles as they are discovered. And so that way, Sam finally gets the array, the original array, completely sorted. And so now she can present me with a bill. So what you need to think is, if each person is going to be charging for the work that they're doing, how much work was done with this algorithm? And that's the analysis of complexity. And of course, what I've done as well is that I've tried to introduce already a technique, which is called the recursion trees, which is a way to visualize recursive algorithms that can help us evaluate as well the running time of the algorithm.
Okay, so that is the whole of the merge sort algorithm. And now we're going to see what comes next. So that's the whole of the merge sort algorithm, and thinking again recursively. So this is the merge sort algorithm that I just wrote again, from that video. So that would be the pseudocode. And again, we realize that the function merge sort is defined by calling the function merge sort, but it's calling it for left and right of the subarrays. And then, of course, that's going to be recursive. So the algorithm has very few lines, but as you can understand, this can take quite a bit of work if you have many, many cards. Oh, yes, of course. I forgot that they need to invoice me, right? And when they give me the invoice, I was very surprised because I wasn't expecting it to be that expensive. So what we're going to do next time is analysis of the computational cost. So how can we actually get a grasp of how much are they going to charge if I do all this subcontracting? Thank you for listening. And I hope that you see the second part.